Yes, you're welcome to the Auto Wheel. This is Kayera Nathan, Group 49. Our project is an autonomous self-driving wheelchair for inclusive mobility at Makerere University. Here are our listed keywords, where we have self-driving wheelchair, computer vision, we have simultaneous localization and mapping, SLAM, graph-based path planning, that is ESTA, we have object avoidance, and we have inclusive mobility in Uganda. From there, I'm going to really summarize on the contents which I'll present today, whereby we shall do a brief introduction and the background of our project. We shall hint on the already done projects in relation to our project. We shall summarize the problem statements and the computational problems. We shall show you our research questions and the relevant objectives, and we shall elaborate the overall system architecture. From there, we shall dive into the individual models, model architecture, and really explain them. So we shall explain our data set and do a simple EDA, the data exploratory data analysis. We shall discuss the results from it and the model training from the data analysis and the model training results. We shall analyze the limitations on our project. We shall do also we shall conclude still and show you some of our future works, and not forgetting references, and finally we shall send some special thanks as acknowledgement to other people. So from here, we are going to the background and the introduction. We all know that limited mobility among persons with disabilities at Makerere University and beyond, and in Ugandan healthcare and other universities, lead to dependence on escorts, delays, and inefficient staff utilization. So currently, the wheelchair which are there require manual control, which limits really independence, especially in crowded and complex places. Recent advancements in computer vision, AI-based navigation, and low-cost embedded systems have made it possible to design autonomous mobility aids. So this project is going to leverage those technologies to create an affordable self-driving wheelchair for inclusive mobility within Makerere University and of course beyond. So the goal is to enhance accessibility, safety, and independence for students and staff with disabilities. From here, we shall do our introduction. We all know that from here, our project is going to leverage components, features, and the technologies which are sensor integration, you can call them sensor fusion, which will combine the RGB-D. These are cameras, camera like red, green, blue, and the depth, that is distance cameras, plus LiDAR, that is the light, and light and light detection and ranging. This light detection and ranging plus ultrasonic sensors. Then you have also the IMU, inertial measurement units, for accurate measurement, perception, and our device stability. We are doing SLAM and localization. So the SLAM, that is simultaneous localization and mapping, to create and update real time map of the university corridors, pathways, and all. So we also have the path planning, which will employ the graph-based algorithm, that is ESTA, an extension of the die-cast plus, to compute the safest and the most efficient routes. Say it's the shortest distance possible when you are going somewhere. So obstacle detection and avoidance. Here we are going to empower a neural network. This is a convolutional neural network architecture, which is YOLOv8, and the predictive model control to force smooth and adaptive navigation. So on the hardware, we are going to run it efficiently on affordable graphical processing unit, that is the GPU, and what is already available is the NVIDIA Jetson Nano. So from there, we have the user interface, whereby we expect to get to develop a mobile application which will allow allow the users to either put commands using text or even graphical or using voice control, in that they do really control they input their destination where they are going, and now they relax until the wheelchair takes them there. So our goal is to provide a scalable, low cost and inclusive mobility solution, empowering persons with disabilities and promoting independence at Makerere University and beyond. So from here we had the related works whereby we got these guys, they are the Morgan State. They developed that AI in 2024. Really, it is working. They used the robot operating system plus the convolutional neural network, and for it was for particularly indoors, and they developed it particularly for the airports, and it is now operating on the airports. Why you didn't use it? It is too complex, too expensive for Ugandan context, and for the beginners it can't be. Also the hardware which it run on, it is high level, it can't run on this. So we copied the ideas, the concepts from them to develop ours. We also have the Morgan Convo system, that was 2020, whereby they used the sensor fusion. Also it was good but not designed for low cost settings like Uganda, it can't be. So we also have the most, those when they use the graph attention network and relational graph convolution network, which was too excellent but require a large amount of training data in millions. And also since there is a big amount of data, it means that it needs a bigger GPU, which is not cost effective for us as Uganda. Now also the bill in 2024, they developed theirs using the YOLOv8 plus SLAM, similar to ours, but for them they were first object detection and mapping. Yes, it was excellent, but poor performance on low power device like ours, which is NVIDIA Jetson. So that one we copied the ideas and we are to also deploy on ours. Then we come to the one which is CDV. So these guys, for them they use the neurosymbolic AI, where they use the GAT and so on. It was to explain very efficient, and it can really map, but the system is complex. If you go there, for us as beginners, we cannot start with it, so we start with a simplest system. We shall advance with time, and it is also expensive, of course. Now here we come, our project, which is in 2025. It is in Makerere University, where I, Kayera Nathan, and a colleague, we are now leveraging the YOLOv8. We are using the ESTA algorithm path, and we are also using simultaneous localization and mapping, SLAM. So we aim for simplicity and cost effective. We are beginners, so our project, our prototype, it might not be perfect at first, but with time we are sure it will be good, and very good, perfect. So here we come to the domain application problem. These are real life problems where you will find that you find dependence. Students need escort for basic mobility. So if there is no one to escort them, they can't go to the lecture room, imagine. So you also have delay, waiting for 30 minutes to 1 hour during peak hours like morning, evening, or even lunch period. Really, it is too frustrating. So discomfort, navigating crowded and uneven path is very hard. In fact, it can even lead to a risk of collision with either objects or walls, and you get injuries. So we go here to the computational problem. We have perception. How can a wheelchair really see and understand its surroundings? Here it is using all the sensors which we have put on in order for it to do what? To really combine and see the surroundings. That's the computational problem. Now mapping, how can it really make a map and locate itself indoor without GPS? Because it must develop its own map. How? That is it. It is its own problem. Now also planning, how can it plan a safe and shortest path to commanded destinations, like you have lecture room, maybe library, dormitory, and so on. Planning. object avoidance. How can it really move safely, avoiding all moving objects like a people, car, and so on, plus also the static objects, which were the walls, we have trees, maybe other objects like stones and so on. Yes. Running on, how can running this AI system, how can you really make it to run all these AI systems in on a very low power and low cost computer? Is it possible? I think it will. That's the competition problem. So we have the research question is on how we have researched it. Here we have, how can a simple AI model enable self-navigation indoors? How can we combine real cameras and sensor data to avoid obstacles? From there, how can basic algorithm like this ESTA find a good path on a campus maps? Here we have research objectives. Our objectives now to build a complete SLAM system for mapping indoor spaces, to train a basic object detection model, that is the YOLO, to see obstacles, to implement path planning using the ESTA algorithm, and finally to deploy and test the whole system on a Jetson Nano, NVIDIA Jetson Nano small computer GPU. Now, research contribution is what we have done, and so far what you expect from us within a later period. We designed and began assembling a prototype of the self-driving wheelchair. Of course, it is in soft copy, so it will be simulated at first, then the chassis will come. We implemented a preliminary SLAM, the simultaneous localization and mapping and navigation model. We started collecting environmental data around the campus for testing. Now we tested all models on the desktop, preparing for deployment on an NVIDIA Jetson. So these models were tested on we are tested in a Google Cloud. Yeah. From here is how we have the system architecture. Read architecture is how I was explaining, but here it is now a systematic way. You have the user interface, whereby the user interface, its work is to enable the user to interact with the wheelchair by either commanding, using either text or a voice note or even graphical, and also make tapping on the stop, emergency buttons, and so on. And we also have the perception layer. Perception layer, it will be having all the sensors around the wheelchair, where you will have the camera RGB and the LiDAR. We have the national measurement unit, ultrasonic sensors to capture the real-time environmental data for object obstacle detection and localization. In fact, you have also the decision and control layer. This decision and control layer, it means that you are going to integrate the YOLOv8 for object detection and the SLAM, that is simultaneous localization and mapping for mapping, and also the ESTA for path planning. So the ESTA algorithm, that is an extension of the calculus, and also do the attentional network, that is the GAT, in order to generate augmented data for effective and maybe accuracy. And here you also have the hardware, which will comprise of the whole chassis of the wheelchair. We have the DC motor, battery, LCD screen, interface, and so on. So here is how the system is being. The user interface, you go to the perception layer, and now the brain will also be having all the YOLOv8 sensor. You have mapping, you have the ESTA, you have also the motor predictive controllers, you have the motor controller. This is from the Arduino, so the motor predictive controller will be integrated into the Arduino motor drivers and so on. So it will go until the wheelchair and the feedback will be done as like this. So from here we are going to dive into system architecture. system architecture for every model. So I have here 3 models where you have the YOLOv8. What it does, it just finds the boxes, finds and boxes obstacles like people, tree, chairs, and so on with a bounding box. So the simple math below it, it looks for image as a grid and predict if an object is in each grid cell. So you have to leverage the center, which is XY with width, then height, and also the confidence, that percentage confidence in detecting how accurate is it. So it will combine on the loss and this. So I'll explain this afterwards. When we go to the path planning algorithm is where you are going to find it find the shortest path from point A to B, like a lecture hall or A to library, or dormitory to lecture hall. So that is the path planning. How will it move? It will locate the shortest distance in terms of cost, obviously. So here is when you have the final destination. Okay, in a simple term, the final destination, go to the actual distance, and now plus the equidistant distance. This is where you are going to find, or you call it the heuristic. Okay, the function is here. Now, as the SLAM, what it does, it builds a map and tracks the wheelchair's location in the same time. The simple idea, it uses sensor data like that LiDAR points and so on to guess how the wheelchair has moved and update the map, obviously. And here it will be leveraging, these are just probabilities, and you will say that the probability of this the position, you call it the pose x at time t with the map. This is the map. It will always go to the measurement, sensor measurement, you call them the sensor measurements, which is the Z. Now it's directly proportional to this. So I will explain this if we have time to come back. Now this is the YOLO model. Now the YOLO model, it is a convolution network layer or architecture where it is having 2 parts, the backbone, the neck, and the head. The backbone, its work is to detect or perceive. It is a perception. It is perceive the structure and the features on the object. If it's your face, they will perceive all the features on your face, and now they converge them to the next layer, which is the neck. Now this neck is now to collect all the information which is provided by the backbone, and it now to do all the filtering and all kind of what in order to make an output which will go directly to the head. Now the head, its work, it will be just to detect and draw bounding box on the objects, and also classify the bounding box and classify, just in simple terms. These are extracts from the inside. I'll explain in detail if I'm given time. From here we go to path planning with the A-star algorithm. The path planning is where you have the environment which is having people, obstacles, trees, lecture, and so on, and you have all the universal aviation vehicle. So this vehicle is now our wheelchair. We have the mission, the destination where you want it to go, and you have the threat information. That's the longest distance, or the distance with hardships, is having obstacle, more things, and so on, or is blocked, or it doesn't know it. So that's the threat information. And now when we go to the autonomous control, it will be having either a human or verification or not. If a human said, I want to take this route by force, it will obey and take it. But if a human doesn't, and just put like I want to go to the lecture hall A, for it to just decide by itself autonomously, and it will figure out the shortest distance to that destination, and it will execute that mission. So when we come to the SLAM, simultaneous localization and mapping, it will be taking in all these 3 sensor data where you have the RGB camera, you have the inertial measurement unit, and you have the light detection and ranging. So they will all feed. I will not explain the whole architecture due to time. And now from here we shall get the 3D map. 3D map, that is the graph whereby it is the map which is developed on that. So from here we go to the data set. Now the data set, we collected videos and images from Makerere University lecture halls and so on. We collected RGB images, but for depth information and sense, like a sensor, ultrasonic and the LiDAR, it is still because we lacked them, but with time we are going to record them. So we started with a few, like 500 plus images, and now collecting more. But unfortunately we are still labeling this data set. So what we did is to go to the RoboFlow. RoboFlow is a website whereby the computer vision people community always put their free data set. So we used that data set. The one we used, it was self-driving, so it had 809 data, whereby we used 80% train and 10% test and 10% validate. So this data set is fully labeled as. Now when you put into the Python code and we did some exploratory data analysis on it, we found that cars are many and also trees. Since it is self-driving, it means that it is on the road, and what you expect to see much is the cars, and now the trees on the sides always. But now for us, we are going to be leveraging more of the pedestrians. So you will find that this pedestrian graph is going to shift up, which is going to make things good for us after training on ours to perfect it more. From here, we do some histogram here, whereby it is having the sensor data from the LiDAR and the ultrasonic. The LiDAR is the one which is in the blue, and ultrasonic is this one. What is this one meaning, the histogram? Like if you have a ultrasonic sensor, from a distance near to zero distance, you'll find that it will detect much, but the LiDAR, it will not detect much when you are towards the object or nearing the object. So the ultrasonic is much effective and precise when it comes to objects which are near the wheelchair. And this LiDAR, it is effective on the objects which are very far from the wheelchair. But when you come to the correlation, you find that they are all almost moving together, so they can be really fused together and combined, and they can calibrate one another since the partner is going like this. And here we shall find on the analysis, like on the sensor distribution, when you say both LiDAR and ultrasonic data range from 0 to 4 meter, mostly around 1.5 to 2.5. Here when you say 1.5 to 2.5, this one is the maximum object detection point. In real life, when you are on a wheelchair and you are near the object, like in 0 meter, it means that you have already knocked it, so there is no point of detecting that object. But if you are like a 0.5 meter or 1 meter away from the object and you are towards it, it means that these sensors are going to detect it and see and stop immediately before even nearing to it. That is what it means, that here when you see more objects. Now this graph means that if like the object distance go far, as long as it goes from farther, it means that there is clear path. You will not see any objects around after like 5 meter. 5 meter you will have a clear path, so you maneuver around in the way you want. This is what I was actually explaining of all. So let's go to this. This is a correlation matrix for the sensor. When you are, let's take like two features. We take like LiDAR distance and the obstacle level. LiDAR distance and obstacle level from here. LiDAR distance, this is obstacle level. Yes, from here. LiDAR distance and obstacle level. Now we are going to take obstacle level in relation to all these sensors. Let's start with the LiDAR distance. We see that it is a negative 0.075, meaning it is slightly negative link, meaning as the LiDAR distance increases, obstacle slightly decreases. So the more the distance to the object increasing, so even the obstacle, it means that it is no longer in our control. So as long as it increases, it will slightly do what? Decrease the obstacle presence from there. So maybe let us take this ultrasonic. The ultrasonic, when you see here from the ultrasonic sensor, it is here. It will say it is a negative 0.0. Ultrasonic, where ultrasonic, it is a 0.02. 0.022. So the 0.022 from here in relation to obstacle level here, it means that it is almost negligible. No relationship all along, because ultrasonic sensor doesn't correlate much with obstacle. And when we come maybe here to inertial measurement unit, there is also a tiny positive link where you have 0.4. It's just a tiny positive, meaning IMU changes a bit when the obstacle appear. So if the obstacle distance go near, there is a change on the inertial measurement unit. All these one, they are all explaining to this, like as the distance increases, there is no obstacle. But now we are relating all the sensors. Now if we are to combine one sensor and another, you combine like ultrasonic and LiDAR, you find that there is no even any relationship between them. So a sensor cannot affect another sensor, meaning they can run simultaneously at the same time and on the same device. So this is from YOLO model. We trained to 100 epoch, but this one, it is giving us, we just selected the one for 20 epochs. So from the training, you find that the train and the bounding box loss, you find that there is a great decrease in the loss. Meaning if the loss decreases, it means that the gain is high. So the object must be learning and very well. It is here, the training bar. So it gradually decreases from a high value to a lower value, which is from 1.4 to 0.8. Meaning the model improves in predicting accurate bounding box locations. The same goes to the class loss. That class loss is where you find that there is a sharp decrease from there. So this it decreases sharply from 4 to 1. Imagine, meaning classification accuracy improves. The model always learns and identify objects correctly. So object classes correctly from here. And all this one, as I have explained. And if it comes to gain, still it will gain sharply, meaning if it is gaining, obviously the model is learning, and the more the accurate it becomes. Yes. When we come here to the training result from this confusion matrix, you'll find that from a high diagonal value for cars, this one you have like the car, you have the car, you have the dash line, you have this road, and you have particularly the tree. So this one, it means that it can identify them very perfectly, although there are some redundancies whereby it can, for instance, it can be in a tree here, it detects the tree, but in the tree it is detecting as a whole, and it is detecting as a sidewalk. When it comes to the background, this line, it means that the background, like for instance here, 214, it is detecting 214 as trees. They are trees, but it is detecting them as background, which is fine. Yeah, background, it can be more vegetation, which is perfect actually. When you go here up, it is 90, 91. there are cars, and if the road is full of cars, it means that 91, it can detect them when the car is not being seen. Well, maybe it is blur, it can really detect it as a background, which is okay, meaning we have attained our goal from the classifying this one. So this one can be outliers, which are very few, and they are not scary at all, actually. When you go here, model selection and deployment, we shall do a step-by-step pipeline where you have the sensor data. You get all the sensors, RGB, LiDAR, and the MPC. So MPC from the ultrasonic, and now go to the robot operating system nodes. Go to the perception where you have YOLOv8. Go to SLAM where you have the map update, and you have the planner where you have the A plus algorithm and the symbolic GAT for generating the argumentative data for correcting and the accuracy correction. So you also have the model predictive controller for control output, and finally you will do control to the motors, meaning it will have to move. So the deployment, it is on the Ubuntu, which is the robot operating system Nutic, then also the interface, which is the tensor engine for YOLOv8, and the latency, we expect it to be below 150 milliseconds on end to end, and on power, of course, it must be utilizing more than 8 hours on a 12V battery. Of course, it must be lithium. Mobile app, we shall do the Flutter, and now a voice, we shall do a voice or even a text for controlling where it is going, so the destination. Now also the live map plus wheelchair status to be seen on the app, and also emergency stop button either on the app or on the chassis of the wheelchair. From there, now we have the limitation is where we have the data limitation is the data set is small and doesn't cover all scenarios. So what is the solution for this is to use the argumentative and the argumentative data that is from the symbolic GAT, and now collect also more diverse videos and around the campus. The model architecture limitation, we have the YOLO model, which is now misbehaving, as you saw that it is detecting a tree instead of a car, so it is not too efficient, and it can sometimes partially hide objects and misclassify some objects. So train for more epochs and also use slightly larger model. Obviously, I admire YOLOv8, which is now the latest, and see if it can really allow to run on this low power GPU, the NVIDIA Jetson. Now the system architecture limitation is you have the system always slow down. We expect it to slow down, of course, due to this, and it can go up to maybe 200 and above millisecond when all the sensors are active. Meaning optimizing this, we have to do the code and apply threading for parallel sensor data processing, in that they process simultaneously without interfering with each other. Now the conclusion say we successfully designed and started building a low-cost autonomous wheelchair. Our initial model for detection and path planning are working in the simple environments, that is Google Colab, and as beginners we have a functional prototype, but there is a lot of error in it, and it is not too perfect as it will, but we expect it to be good with time. Now the future works, what we are going to do to improve the object detection accuracy by collecting more data. So here we have to test the complete system on the real wheelchair chassis on campus, of course, and add a voice control feature to a mobile app to ease easing the user. Explore how to make the system work outdoors by adding GPS, because it cannot map the whole campus. It needs some GPS on outside environment when it is not inside. The differences, of course, with the YOLO, we got the robot operating system, we have the rapid, then we have the all from the ultralytics, We have the motorway with these projects as seen here, and of course we can't fail to thank our Dr. Galiwango Marvin for making us have sleepless nights. We thank you for that, and we always thank the college for giving us space, the library, laboratory, in that we can access read. Also, the open source systems, open source community, more especially the Ultralytics, where I found the YOLO and also the robot operating system, and also as open source like a collab and so on. Really, I'm thankful for them. Not forgetting my classmates. Also, they can be headache and they can really annoy, but really, this is life and the project is going on, and we expect good results from there. So, thank you for coming.